Okay. Well, thank you very much for the invitation to visit. I'm very excited to be here and to be telling you a bit about the work that my collaborators and I have been doing on developing new tools using generative AI for fundamental physics. And I thought I would just start, actually, so thank you very much for the kind introduction. And I had a slide just to introduce myself a bit, but I can now more or less skip this. And I guess actually, well, during my undergrad, I did neutrino experiment on the NOMAD collaboration, but I didn't include that here. I actually did a one-year master's in Cambridge. That was my first real, I would say, real taste of research doing X-ray astronomy there. So I actually have a little bit of history as an astronomer doing that stuff. And then, yeah, for my PhD, I did a lot of formal theory, especially matrix models and minimal string theory, which I'm told is making a comeback now. So there's a younger generation of students that actually came and found me at KITP last November, asking me questions about, you know, you're old when like you don't remember papers you've written from. Right? Yeah, so that's happening, and then as the LHC was turning on, I got very excited about that and branched out, moved into phenomenology with work on SUSY breaking in metastable states, general gauge mediation, and since about 2010 or so, I've been heavily into collider phenomenology. I'm also branching out into flavor physics. Of course, the discovery of the Higgs and its implications for supersymmetry. That's all just to set the stage for what I've been doing since 2017 or so, which is what I'm here to tell you about. So I got very interested in, you might say, yeah, so the evolution of this has been towards, you know, all these ideas of what could be at the LHC have sort of, you know, led to more and more limits, and so I got increasingly motivated, let's say, to think outside the box. And when I found out about actually from a former student of mine, what interesting things were happening in machine learning, at first my reaction was, oh, come on, this is not physics, don't bother me with this stuff. But as I got more and more into it, I realized what a powerful tool this could be, and maybe this is what we need to break through sort of the things we're stuck on. So since 2017, we've been building up quite a research effort at Rutgers, both myself and my colleague there, Matt Buckley. And this is our current group with a number of postdocs and students, and some recently graduated students still collaborating with Anna and Ronit. And Ian is is going to defend in June and is going to Fermilab plus Alabama joint postdoc. So yeah, so we have a worldwide effort developing ML applications for fundamental physics, and just to motivate why we're doing this, and so I was trying to use my my history and my trajectory a bit too. So why work on ML for HEP? I think we have to appreciate in our field that we are stuck on some very old problems. And so I actually asked Gemini to make this for me, and then checked it. So it's been checked. So there's a reason for each one of these. So this is a timeline of how long a problem has been open in our field up to the present, you know, and the oldest one, maybe according to this chart at least, is quantum gravity, going back to Einstein and others. And maybe the newest one, our newest problem from this chart would be neutrino masses. You know, what's the origin of those in the Standard Model?
It's obviously not true, right? People were thinking about neutrino masses from like 1960s.
Sure.
This is where they was discovered, right?
Okay, so I'm no historian of science, so this is when they were discovered. That's when you could say it became a really sharp puzzle. But anyway, so these are the kind of things we are working on, and it's a very hard field. We're not in an era where there's rapid movement on these things. And it's not helped by all the places we're looking, at the LHC, at direct detection of dark matter, that all the searches we're doing keep coming up empty, and we have increasingly stringent limits on our favorite models. So, you know, a lot of us are feeling, oh, are we stuck? And I really like this quote from Freeman Dyson, and I was careful to source this, so you find lots of fake quotes on the internet. But he actually did write this in this article, Scientists as Rebel, that according to him, the great advances of science usually result from new tools rather from new doctrines. So I think that's what motivated me in 2017, and increasingly, to think maybe the top-down approaches are missing something crucial, and what we actually need is more bottom-up guidance from the data, even as theorists. And so there's two ways you could go with this. One is that you need new data, so new experiments, and that's been a very fruitful direction for theorists and experimentalists of proposing new, for example, new tabletop dark matter experiments that would probe different forms of non-traditional light-dark matter, and also proposing or contributing to the design of future colliders and future detectors. So that's certainly a fruitful avenue, is to have new experiments that give us new data that might break through. Of course, for a lot of these things, we're going to have to wait. Many of us will not be around when they're finally built, so that's a daunting proposition. And a lot of these things are also sort of shots in the dark, fishing expeditions, and they may turn empty. So there's no guarantee of success for any of these things. That's built in, I think, to everything we're doing. And so option two, I think, is also promising. That's what I want to focus on in today's talk, which is maybe with the data we already have, or we're going to collect in the near future, the data from the LHC, data from these big galaxy surveys, SKA, radio astronomy, so things that are planned, coming online, we don't have to wait 40 years for. There's these enormous data sets, and maybe what we need are new tools and new instruments to dive deeper into the data that we are going to have or already have. So that's what I view these machine learning and AI tools that we're developing as sort of their new instruments, but not for not like a microscope or a telescope, but for the data itself. So we're developing new ways to analyze and to get much deeper into the data. So that's what this talk is going to be about. Okay, so of course we all are increasingly aware. I'd say every time I give a talk like this, there's even more excitement, so the hype just keeps building. We're clearly at a historic moment of technological advancement. This was recognized very presciently, I think, by these people already as early as 2020. Okay, 2020 is only 6 years ago, but it feels like a long time ago. So that if you just scale up what you have, what they had at the time, they realized that there are predictable scaling laws that would lead to ever better performance. And so we've been on that trajectory. The big companies like OpenAI and Galactic have been on this trajectory ever since, and we're increasingly benefiting from or suffering from the fruits of these scaling.
This is Jared Kaplan. No?
This is our colleague Jared. Yeah. So that's by now a classic paper pointing out empirically that these scaling laws seem to exist. So we're seeing these remarkable achievements by AI systems, doing well on math, on high-level math exams, coding benchmarks, different types of software engineering benchmarks, and we have people winning Nobel Prizes that either use AI to do remarkable things in chemistry, biology and chemistry, or physics prizes going to fundamental advances in AI.
So that was the protein folding?
These are the DeepMind protein folding guys. Yeah. So what I'll be talking about today is more in the vein of the DeepMind people, which is how do we take the AI algorithms that are being developed and repurpose them to do cool and interesting things for our field, which is what the AlphaFold people did for protein folding. Okay, so what's driving all this progress is also relevant, I think. So we've got at the foundation big data. So I don't think any of this AI stuff could have been done without having access, to the whole internet. So that's predicated on the availability of an extremely rich and available data set. And that's where I think high-energy physics has a lot of overlap, because we also have enormous data sets, and very rich, complicated, interesting data sets. So built on that, you want to get as much as you can out of them. And what people have found is that neural networks are extremely powerful function approximators. They are universal function approximators. So you can feed all this complex data to them, and well, if you just feed them to a straight up neural network, you might not, like a simple one, you might not get all the information out. So people have also developed smart algorithms that use neural networks in various parts of them, and you've probably all heard of the transformer network by now, but also things like diffusion models. So they're built from neural networks, but then they also involve another layer of sophistication and cleverness for how do you train them, exactly how you parameterize things, how you feed the data to it. So all these things are what ML research entails, and out of all that, we get these amazing things like ChatGPT. Okay, so what this talk is specifically going to focus on is how we use these things called generative models to do interesting science. And so these are a key building block also of the chatbots and the agents. And so I thought it'd be important to maybe explain a bit, in case you're not familiar with how these things work. So just at a very high level. So what these generative models are, they are functions. You can think of them as functions, f theta. Here theta refers to the parameters of the model. So they're functions with parameters that we fit to data. And these parameters are usually parameters of a neural network. And what this function does is it transforms a random noise, usually sampled from some simple distribution like a unit normal Gaussian in some number of dimensions, to data. So we want a function that transforms noise into data. And the idea is that if you learn this map, so if you learn how to morph a bunch of Gaussians into stuff that resembles the data, then you can generate more data, more fake data. And what does it mean to resemble the data in this case? The rigorous criterion here is that imagine that the data has a statistical property that it's IID, and it's drawn from some underlying distribution P of X, which we don't know. So all we see are the samples of the data, right? And think of like a histogram or something. So we just see samples.
Excuse me, I
Please,
don't
yeah.
understand. If you have some kind of a noise which carries very little information, how can you, whatever you do, can you transform it into something which carries a lot of information?
Great question, yeah. So that's exactly the magic here, is that although all the information is in the distribution of the data, and so you can, as long as you encode the transformation, I'll have it on the next slide, like the Jacobian formula, as long as you encode the transformation of the random Gaussians to the data distribution, that's what's being done by this function, you put the information in, basically.
Isn't it out of blue air?
The
How
information is
how
stored in
can you-
theta. The information's in theta.
The
All of physics and information is in theta.
Yeah, what I was
That's
trying to
right.
say is that, so what we do is, so we imagine that each data point that we have, this is the assumption, is uncorrelated. They're all independent draws from some underlying data distribution that we don't know. We're trying to learn that distribution. So think about like if you just bin one-dimensional data into a histogram, then you try to fit that with some functional form, and then you've learned the one-dimensional distribution. So this is what the generative models are trying to do in much higher dimensions, where you can't just make a histogram. Yeah.
That's assuming that any sampling give you real data. What about impurities? What about disorders that normally people try to get rid of?
Impurity. Yes. So
Well, disorders that normally give you a histogram of the data, but you normally want to get rid of it. It
Good,
doesn't
so-
contain any information.
So I'm assuming I'm assuming that the data we have is the data we have, and if you clean it, you can purify it, whatever you want. But the general problem statement is going to be this. So somebody hands you some data, and either they clean it up or not, but then you learn if it has all these impurities, then you will learn the distribution of those impurities. Yeah, does that answer your question? So, okay, so yeah, so the goal is to turn.
There's one more question.
Oh, please, yeah.
I just want to make sure I understand the diagram. So you're thinking of the green thing as kind of a function, and you're feeding it the red stuff, which is very noisy data, and then it's spitting out what? The blue is somehow the output, but what is the blue?
Okay, yeah, so what we have, yeah, maybe I should focus on this. So what we have is a collection of data points, like some scatter, and they follow some distribution, and we'd like to learn that distribution. So what we do is we try to map the random noise from a distribution we know to match the data distribution. So just think of it like a morphing. And then I haven't said what the exact objective is here, but usually you would maximize some likelihood of the model over the data.
In other words, the left side is like, you're like, oh, I think it's a Gaussian, so here I'm spitting out random samples from a Gaussian, and then you're looking. Okay.
Yeah, and then what you have, you don't have an exact pairing, but you have the data which follows some other distribution. Yeah.
Okay, I have one more question, because I don't understand this magic. Let's take the particular example, which was not particularly much data. People knew that atoms are stable, and this was in contradiction with the Maxwell laws, okay? So that was all, okay? And how this procedure would generate old Bohr's quantum mechanics? How these two facts, Maxwell equation plus stability of everything we see around, would generate I don't speak about the entirety of quantum mechanics, but just the conjecture, beautiful conjecture of Bohr that electrons move along some subset of orbits and they don't radiate.
I think that's a tough question. So, I mean, I would say this is not a panacea. So this is going to help us with certain problems, and maybe early quantum mechanics was not one of these data-rich settings. And maybe there's a way to turn it into that. So this is not going to be like a perfect solution to everything. Okay. Yeah, so I'm not selling it as that.
So it will work only when you have a complicated mass of data and you need sort of order it out.
Well, at the end, I'll present an example where we're using the generative AI as a helpful assistant to do more traditional theoretical physics. So maybe that'll be a way in for this kind of stuff. But that, yeah, I'd say the bread and butter is, imagine you have a very complicated data set, which, with modern computing, we're definitely in a different regime than we were in, 1900s.
Yeah.
So that's where we often find ourselves these days.
By the way, you mentioned the magic of ChatGPT.
Yeah.
You know that till now, it produces lots of wrong answers. I check it myself.
Absolutely, and hold that thought till the end, and I will commiserate with you.
Misha, you're training it. That's what you're doing.
Actually,
You're training it. It's learning from you.
It doesn't take into account because once it make a big mistake.
Time is short.
Okay. I just said the first time I ever gave a talk here, I still remember it. It's one of the first seminars I ever gave as a graduate student. It was on ISS, and I remember I think Misha and Vine and Arkady. I think they wouldn't let me get past slide 3. So I'm on slide 9. So
I'm sorry, I glue my lips.
No, it's part of the experience. Good. Okay, where was I? Oh yeah, I think it's important to understand how these generative models work, because everything I'm going to talk about afterwards is based on this. So please ask all the questions you have, and hopefully we can all get on the same page. So what we end up with when we fit these generative models to the data And so these are like totally unsupervised in the machine learning language. So there's no labels. All we have is raw data, and we learn the distribution. So once we're done, we get a function f theta that you give it random sample z from the Gaussians, and it produces data points that follow the data distribution if things are working. And this is what underlies all the chatbot technology. So ChatGPT is the is the classic example where it's been trained on the distribution of language, treating language as a random process. Well, it's random but with a lot of structure. So it's the balance of these two things that allows ChatGPT to work so well, as opposed to previous attempts at natural language, which are more rules-based. ChatGPT has this inherent randomness, so it learns to predict the next word as a probability distribution given previous word from the distribution of words that it finds, sentences and language that it finds on the internet. Midjourney is a image generating app that has a similar property where you give it a caption and then it learns that it's been trained to produce images that follow the conditional distribution of, from caption image pairs that it also found on the internet. Yeah.
So this is a description of pre-training, but a lot of the magic comes from post-training, right?
True.
These things are not just next word generators.
Absolutely, absolutely. Yeah, so I'm oversimplifying it a bit, but this was like ChatGPT 2 or something, GPT 2.
Okay.
Yeah.
Then yes.
So, and then, yeah, all the amazing capabilities that we are benefiting from now are increasingly coming from the fine-tuning steps. Yeah, so I'm simplifying that. Thanks. Okay, notice that both actually are what we call conditional generative models, where you get to feed an input here through the conditioning, and then it produces a conditional density. So the generative models are typically flexible enough to also learn conditional distributions. Okay, so the key class of generative models that's found very nice applications to particle physics and fundamental physics is something called the normalizing flow. And this is actually not what ChatGPT is based on, but it turns out to be a pretty good fit for our kind of problems, at least in my experience. And a normalizing flow is a more restricted type of generative model where what you have is an invertible map. So you have an invertible map between noise and data, so it can go in both directions. So that's a strong assumption and constraint to put on the model, but that gives you some advantages. So if I go in this direction with this map, I'm generating, it's a generative model. And if I can also run it in the opposite direction, starting from data, I can recover noise, but then I know what the density of the noise is. So I have this Jacobian formula here, which lets me read off the density of the data. So this is a case where I have both a generative model and what's called a density estimator. So given a data point, I can also read off its probability density. Yeah.
Yeah. So I'm having trouble integrating the red one as noise. Shouldn't I just view them as, basis Gaussian distribution? I try to work out the grid map to the data I want. So the red one is just some standard basis distribution I put in for the system.
Yeah, I guess calling it noise is maybe from the ML literature. They call this noise to real. So maybe that language is confusing.
I think that causes many questions.
Yeah.
It's kind of standardized.
Yeah,
It's just standardizing.
Yeah, just standardized base distribution. I work out a map to data.
Yeah.
And
So just think of like you can transform any one-dimensional distribution to the uniform using a CDF. So that's a standard trick in one dimensions at least. So it's the same thing here in higher dimensions. Yeah, we could call it the standardized distribution. Yeah. Thanks. Okay, so normalizing flows are actually going to be a key hero of the story today. Good, so could generative models be the new tool that we need to break through? So maybe this is the way that they're going to help us. Maybe this is the future. So a lot of people are speculating that the generative AI, which are built out of generative models, will get more and more powerful, and eventually we just sit back, go to the beach or whatever, feed the data, we'll feed everything, data, ideas, Lagrangians to the chatbots, the agents, and there will be scientific results. Okay.
Could I ask you something?
Sure.
When you apply it to, say, searches of physics beyond standard model, right? There could be some signatures at LHC or any other experiment which are unmistakable, and if you see it after acquiring a lot of data, you wouldn't need like a lot of processing, right? So if it's some heavy Z prime particle with a few TeV mass and you have a bump in the distribution of mu plus, mu minus, probably you can do it with any other technique, or you have a proton decay that gives you pi zero, and then positron, you will also see it with a few events and you'd be convinced, right? Would this be most useful for the cases where you have lots of noise and the data sort of new things hidden behind a lot of background? And
so the anomaly detection example I hope to show is going to be exactly that, where, so this is going to be useful for hidden stuff, I think. Yeah, so model independent. So we assume that this will, we posit that the data is big, vast, and complicated enough that if you don't look in the right places, you could miss something. Yeah. So if you just turn it on, you collect the data, and it pokes you in the eye, you don't need any of this. Yeah. So I'm operating under the assumption that we're increasingly not in that situation, at least at the LHC. But,
yeah, because this makes a big assumption that there is some hidden signal which is very hard to see, right?
Well, that's what we're trying to develop tools to see if there's anything. We don't know until we look.
And since we're at that, there is a lot of development at LHC with the spectroscopy of multi-quark systems with, that this is where I think there might be some applications of AI, just because there is like one resonance after another being discovered, and since many of us are just focused at the TeV scale, nobody pays attention, right? So maybe there is some playground there to learn about standard model per se, right?
Chemistry would fit.
Yes. Well, we already saw the Nobel Prize in chemistry.
Multi-molecules, long chains,
Okay, sorry.
Okay. So this might be the future, but I don't know. We're certainly not there yet. So where we are today, this is where we're making exciting progress now, is what we are doing is we're taking the building blocks. We're not just feeding everything to Claude or something. We're taking the building blocks that go into these powerful models. The building blocks are what make these models so powerful. Things like transformers and flows and you name it. And we're repurposing them for custom analyses and objectives for our data. And so that's what's shown here in this schematic. So we're rebuilding, we're sort of building our own tools and applications. That's where the creative aspect of this and the intellectual innovation comes from. Okay, so, and increasingly we're also doing this, and I hope to be able to tell you something about that at the end. So we're also now doing the same sort of workflow of designing custom AI solutions to our problems in collaboration with these generative AI agents. Okay, so this is an outline for the rest of the talk. I'll try to squeeze this in half an hour. I'll see if what I can skip along the way. So yeah, I wanted to start with maybe the simplest example of how you would use generative models to help with big data analysis, and that's something called surrogate modeling, where we use it to speed up simulations. Then I would turn to the flip side of this, so density estimation, and take maybe the purest example of that, where the data distribution itself is an interesting observable. And then the example I'll give is work we've done to turn the phase-space density of stars that you can get from the Gaia Space Telescope into a measurement of the dark matter distribution around us, three-dimensional dark matter distribution around us. And then, time permitting, I'd like to also talk about using both generation and density estimation for anomaly detection with applications to model-agnostic searches for new physics at the LHC. And finally, this is what I've been working on in the last few months, is collaborating with Claude Code to do actually some more traditional theory work. Okay, So first application. So this is, this is a snapshot or a schematic of what surrogate models are. So we all know that simulations are key to science and to what we do. They're where theory and experiment can make contact, and they're essential for all kinds of measurements and searches. But often the simulations that, especially in our field, that are extremely accurate are also extremely slow. So there's a strong incentive and need to speed up existing simulations. And so the idea of surrogate modeling is that we could maybe generate a smaller sample of slow, using the slow simulator, a smaller sample of simulated events, simulated data, and then we could train a generative model on that to be a surrogate. And then now that surrogate model has learned the distribution as best it can from the smaller number of simulated examples, and then it can be a fast but approximate generator for that same simulation. So you won't get exactly the quality that you do in the full simulation, and you will miss out maybe on tails and things, but this could be a powerful fast simulation for the right application. Yeah, question?
Can you say a little bit more about what kind of simulation we're talking about? So, for example, if I'm interested in the ground state of a Hamiltonian, okay, then
yeah. Okay, so good. So this is a general framework. So after we train it, we can use the surrogate emulator as an emulator for the original simulation, and we get a distribution from P surrogate that is hopefully close to the simulator distribution. Okay, so this is the prime example that I would tell you about is surrogate models for calorimeter simulation at the LHC. So the prime tool for how we simulate detectors at the LHC is something called GEANT4, also in many other experiments, also in nuclear physics. So GEANT4 is this general purpose toolkit for simulating particles propagating through matter. Medical physics too, so all sorts of domains, but it's very slow to run. It really, propagates every particle and considers all the nuclear physics and electromagnetic physics that could happen along the way. So you get these big trees, and it slows down, as the tree gets bigger and bigger. So this is the main, the single biggest computational bottleneck for Atlas and CMS in particular, and without further R&D in the LHC era, it's going to overwhelm their compute budget. So the kind of R&D that we're doing here is in service of that. And so there's been early work from using something called generative adversarial networks, GANs, and my own work from 2021 with our postdoc at the time, Claudius Krause, applying normalizing flows to this problem that showed that you could use generative models as good, fast, and accurate surrogates for GEANT4. And so we were able to achieve orders of magnitude speed up with, especially with the flows, with extremely good quality. So it matched all the metrics we looked at, got very good matches with the GEANT4 reference. And so this motivated us to organize a data challenge, a community challenge. So this is something I've been very active in. So we called it the Callow Challenge, and it ran over the course of 2 to 3 years, 2 years or so, 2022 to 2024. We gave people 3 different training data sets made from GEANT4 of increasing dimensionality. And the goal was to train generative models on this to reproduce their distributions at the voxel individual cell or voxel level. So these have dimensions. These are probability density estimations and generative modeling in space dimensions of like 100 to 10,000, so 10 to the 2 to 10 to the 4. And it was, I would say, very successful. We got over 70 participants who submitted over 30 different approaches for these 3 different data sets. And we produced a community document that you can look up here that is a compendium of a bunch of different ML approaches for this problem. And some of the best approaches that use really cutting edge stuff like diffusion models, something called flow matching. They produce basically like almost perfect fidelity to GEANT4 while getting a significant speed up. So these are ideas that are being explored now inside of Atlas and CMS to see if they could help with the next generation of fast simulation. Okay, so I think I will probably skip this. So after, okay, after it's very hard to skip anything. These are all my babies. Okay, so after that success of applying normalizing flows and surrogate modeling to Jan4, I searched for other applications. So that's the beauty of this kind of work. Is tools are they're like normalizing flows and whatnot. They're like very powerful hammers. They just come from some other place, and you have this hammer now. Once you learn how to use it, you start looking for nails. So another place where we, I think, had some success is in a completely different area, so pulsar timing arrays. So I'm not an expert from this field at all, but this is a very interesting avenue from radio astronomy to look for something called the stochastic gravitational wave background, and eventually other things like binary supermassive black hole systems that produce periodic single frequency gravitational waves. And so currently what they think they can see at some significance is the stochastic superposition of all these binary supermassive black holes surrounding us. And they each produce gravitational waves at some frequency, and then they all superimpose. And what we see is this stochastic gravitational wave background, which is described by some power law. And we can do all this using a pulsar timing array, so the very accurate timing of millisecond pulsars in an array can give you this characteristic power law shape measurement, and also a characteristic correlation between pulsars in different parts of the sky, so their angle and the statistics of the pulsar residuals are correlated. So that's this famous Helling-Downs curve, which was observed by Nanograv at some significance relatively recently. So that was a big deal. And where we found potential for ML to help with this was when they actually do their inference. So the parameters, the simplest parameter space they do their inference in, has a power law slope and an amplitude to this gravitational wave background. And the posterior inference, they use Bayesian statistics. So this is a posterior map, a posterior likelihood. The way they do it traditionally requires something called MCMC, and that uses millions of slow likelihood calculations to sample this posterior space. And so it's a matter of fact that one of these plots can take weeks to produce. So the bottleneck is they have to invert, it's a Gaussian likelihood model, and they have to invert large matrices over and over and over again. So just that simple act of having to do matrix inverses, millions of matrix inverses, each matrix is maybe 10,000 by 10,000, slows down the whole thing. So what we found is that you could instead train a single normalizing flow on samples. So although the posterior is slow to learn with MCMC, or to estimate with MCMC, samples actually are very quick to generate. Because to generate a sample, you don't need to invert the Gaussian matrix, you just sample from a Gaussian. So you can produce training data for a normalizing flow very cheaply, and then the training takes, maybe a day, but it's what we call amortized. So you just do it once and for all, and then you've paid that cost up front, and now every subsequent plot you make that looks, is like this, would only take a matter of seconds. So you can take this calculation from a matter of a week to, the training time plus a matter of seconds. So that's a potentially interesting, powerful tool for the pulsar timing array collaborations to use, and this was done in collaboration with a bunch of postdocs and Steve Taylor, who was at the time the spokesperson for Nanograv. So,
how do you know that you're getting the right answer?
Good. So that's what this sort of calibration plot is meant to show. So you're not getting exactly the right answer, as you can see. There are tricks red here is what we get from our flow, and MCMC, which is like the ground truth, is shown in blue here. And what we can do, though, is we can also do tricks to reweight the distribution and improve the accuracy. But in general, you have to maybe extrapolate or calibrate to be able to trust this. So yeah, what I think this could be useful for inside their collaborations is for fast studies. Often they have to do simulation studies and things, and each study they do might take a week to wait for a plot. Then they can do fast, like quick and dirty studies. Probably for the final plot, there'd be the MCMC gold standard, but this could be like a surrogate for quick studies.
Is there anything that's come out of this that, they couldn't do before, right? For pulsar timing, there's no rush, right, for that crowd. So what science did this enable? Or, you're kind of saying, well, I can do some, I can analyze my data faster, which I agree. But what has it enabled for them?
I'm not inside Nanograph, so I'm not entirely sure. But I mean, so we're also currently working with the head of their, I think the head of their new physics working group to add more parameters to this. So not just the SGWB parameters, but also breaks in the power law that could be from early universe phase transitions and things. So it might allow for more quick studies of sensitivities or stuff. Maybe there's no rush, but this could allow you to do more. But yeah. Good. So that brings me to the second thing that we're doing, which is using these flows and generative models in the opposite direction to do density estimation. So this is actually something I think I'm most excited about because it's an example of open data analysis that we're doing as theorists using powerful machine learning methods that we developed ourselves. That's, I think, shedding new light on a problem we all are interested in, which is dark matter. So this is the data set we're using. It's from the Gaia Space Telescope, which ran for about 12 years. Recently, literally ran out of gas, I think. So it has these little thrusters that keep it in place at some Lagrange point, and it ran out of the gas for those thrusters. Very sad. Currently, it's on the third data release, and there's expected to be one or two more. And what this can do for us is it can get us the full phase space, so the angular positions, but also the velocities on the sky, also the photometry, and then the distances and the radial velocities, so the full 6D phase space of, you get this reduced subset for over 1 billion stars in our galaxy, so about 1% of the stars in our galaxy. And for a subset of closer in stars, so within about 4 kiloparsecs of us, about 30 million stars, you get full 6-dimensional phase space. So I think that's remarkable. That is an incredible data set and an incredible observable, and which we can now learn. So 6D is too high to do histograms for, but with normalizing flows, we can learn this 6D phase space density extremely well. So here's a plot showing different plots showing we fit a normalizing flow to the phase space density to the stars to their 6-dimensional kinematics, and these are plots showing the quality of that fit. So these are 1-dimensional marginals of the 6 positions and velocities, showing good agreement of the flow to the data over many orders of magnitude. And this is a 2D heat map for stars within 3 kiloparsecs, showing their number density across the, these are galactic coordinates. And so we learn a smooth version of this 2-dimensional histogram pretty well. And so what can we do with this? So the idea we had is that we could first, so we fit this flow to Gaia stars, and this function, which gives us the phase space density, has incredible physics in it. We learned this phase space density, and it's a fully differentiable function. And so we can plug it in to the collisionless Boltzmann equation. So the stars are believed to be in approximate equilibrium with each other. They've been orbiting and doing their stuff for billions of years. So most of them are thought to be in pretty good equilibrium with each other. The last major merger was a long time ago. So to a good approximation, the phase space density should satisfy the collisionless Boltzmann equation shown here. And so now the key thing is that we can measure F for the first time with these flows, and Gaia data, we can measure F from the data. It's differentiable. And then the thing we don't know is the gravitational potential. So we can use this to infer the gravitational potential as a three-dimensional function everywhere where we have the 60 stars. And so so we parameterize that with another neural network, and we solve this differential equation as a simple MSE loss, mean squared error loss, a simple least squares loss. And that's an example of something called a physics-informed neural network. So this is a general technique that people are using to learn solve all sorts of differential equations. So then this phi is a neural network. It's also differentiable, and we can then extract from it acceleration fields and also the mass density. So that's, I think, yeah.
So the normalizing flow seems to play a key role here, right? If I understand that the green box is a mapping from standard distribution to the data, so the green box contains information of phase-space density, right?
Yeah.
So what does the role of being able to invert matter? How that normalizing flow has this feature of being invertible, right, in this green box?
So all the information is contained in the Jacobian, so the transformation. So this green box is the function, and when we invert, so I could go back here to show, yeah. So when we invert, we can read off the density of any data point because we know the base density, and then this Jacobian comes from this function.
From f theta or f inverse
theta? Theta z, that's this, well, the inverse of that.
Yeah, so inversion matters here. So that's your phase-space density. So you're directly using this feature for.
That's right. So once we invert, we read off what the base density is because we take a data point x and we map it back to the base distribution, the standardized distribution. We get its standardized density, and then the Jacobian factor gives us the complexity of the data.
Yeah. Thanks.
Sorry, go back to the where you were, yeah.
Yeah.
No. Yeah, in the red equation, how do you get the gradient of phi from that? Because it seems that it only would give you one of each components, the one.
Oh, great question. Yeah. So that's also one of the things we solved. So excellent question. So indeed, this looks like one scalar equation for three unknowns, ax, ay, and az. But what we realize is it's actually an infinite number of equations for them because it's true for every velocity v. So these only depend on the position x, so the three-dimensional position. The acceleration field, the gradient of the potential, so it can only depend on the three-dimensional position. It cannot depend on the velocity. So now we can actually sample like all the different velocities at a fixed position to our heart's content. And so we can get a hugely overdetermined system and then do a least squares fit to determine grad phi.
Just because there are many stars with different velocities
Yeah,
around
even at a
any
given,
point.
within a small ball around some position, there's a bunch of stars that are moving in different directions. Yeah.
But don't you check some self-consistency, your phase-space density distribution when you integrate over, you get the density, things like that?
Yeah, good question. So I think if I understood you correctly, how do we ensure that we get the right number density from this?
Correct. Because
so actually what we do...
equation, there's a particle distribution, and everything is connected.
Yeah, so what we actually do is to help ourselves in that regard, we split it up into two normalizing flows, one just for the number density, and the other is the velocity conditioned on the number density. So we're guaranteed to get the number density right. And also then we can sample from the other one to get a bunch of velocities.
The standard technique is that because you already know that you are making the assumption for the steady-state equilibrium, right? But you have a system of three differential equations. Basically, you can solve them self-consistently. I mean, I'm not so sure that compared with the standard technique, what you get from this method.
Good. I'll show you that in a couple slides, the comparison with the standard. So by which you mean like genes analysis.
Exactly.
Yeah. So I'll show you the comparison. Yeah.
Sorry, probably a collision question. Going back to collision with Boltzmann equation.
Good.
It's approximation. So in general, there is also collision integral at the right-hand side.
Yeah.
What is the estimate of this collision integral? Because again, you are dealing with large amount of data.
So these are stars. So I think to a very good approximation, you can ignore the collisions of the stars with each other. Space is vast and empty.
And
we're all alone.
The error of doing this is much smaller than anything you are doing.
Yeah. But yeah, good question.
Fortunately,
more important is
very
the disequilibrium effect. So there's a DFDT also that we're dropping. And there is about, I believe, maybe 10% is the number people go around for the amount of disequilibrium in the stars. into residual effects from mergers and something called a Gaia sausage, for instance. So anyway, but yeah, so our results may be correct, to like some 10% level because of that. Yeah. Okay, so let me show you what those results are, and then also answer your question in the back. So this is our fit for the potential, phi of x, and we compare it against the reference potential from one of these astro packages where astronomers have sort of done a bunch of different fits with different data sets, and I think some eyeballing, and basically no error bars. That's okay, so I won't say anything about that. But anyway, that's our reference. Is the dashed line is this Milky Way potential 2014 from the Galactic package. It's easy to plot. And we see we're agreeing with it more or less, and also we're recovering the expected symmetries of the problem. There should be like an azimuthal symmetry. Sorry, so this is looking down on the galactic disk. So Z is the height off the galactic disk. Y is towards the galactic center. X is in the direction of rotation. So this is looking down on the galactic disk. And this is the another view, like a side view, where this is the distance to the galactic center, and this is the height off the disk. So you expect there to be like a north-south asymmetry. You expect there to be an azimuthal symmetry. So we're more or less recovering that from our fits. We also can get the acceleration fields. They agree well with Milky Way potential 2014. And here we're doing a more stringent test. So at specific positions of different binary pulsars, there have been other measurements of galactic accelerations using these binary pulsar timing. And so that's from these papers, Donlin et al. And Moran et al. And there's 24 of these measurements that we can compare with. Ours are shown in black. And we can see we're generally in good agreement with these binary pulsar measurements, which is good because they don't assume equilibrium. They're just directly measuring the radial acceleration at these positions. We get a three-dimensional acceleration field measurement, AX, AY, and AZ. But at those points, we more or less agree. There's four that show some disagreement with both previous measurements. This could be evidence for disequilibrium around those points for whatever reasons that would be interesting to understand. Okay, the real money clock is here. So this is the mass density. So we can now take another derivative of our learned potential and return to the mass density. And so this is what you see is, this is all from the data. No model was put into this. Well, the neural network is a model, but it's a very high parameter model. And what you see here is a plot of the mass density, the total mass density, as a function of height off the disk. So going through the solar location. Solar location is here. And measured against that are the best estimates for the contribution from stars and gas. That's shown in blue. And when you subtract off the stuff you can see, you're left with a residual density, which overall is non-zero. And you can basically ask, what is that? Well, it varies with the height off the disk, but if you just assume that it's spherically symmetric for a moment, then you can get a single number out, which is very consistent with previous measurements of dark matter density. So 0.3 in particle physics units.
What if you don't assume that it's spherical?
Well, then you get this.
But in terms of the prediction for the local dark matter.
Good. So if you don't average anything, then this is what we find at the solar location. And actually, this is already averaged over azimuthal. So what we get exactly at the solar location, no averaging, has a pretty large error bars. Yeah. So not a sensitive measure. So only after we do some averaging do we get such a small error bar. So yeah. But this is a technique which I think will improve with DR4, et cetera. So someday we may hope to be able to measure the dark matter density exactly at the solar location with no assumption or no averaging. Yeah, and sorry, just to answer your question in the back, this is a comparison with previous measurements. I think all the blue squares here, I believe, are, or is it the triangles, I forget now, are genes analysis measurements. And the thing with genes analysis measurements is they usually only, they make assumptions and they do parametric model fits. So ours I view as a more model-independent measurement of the same thing that also gives you the full, with large error bars, the full three-dimensional map. So yeah, we mostly agree. Actually, we're kind of on the low side compared to all the other measurements, which is kind of interesting. But yeah, okay.
I noted that the phase-space distribution function had no dependence with time. So are we missing anything by not having a temporal derivative in the Boltzmann equation?
Where would that? Yeah, so that's the assumption of the equilibrium collisionist Boltzmann equation. So we make the assumption of equilibrium, and the time derivative drops out. And that's the thing I was saying is believed to be accurate to like 10%. So yeah, there's no way to include the derivative because we don't have time snapshots of the phase space, the stars, over the timescales of tens of billions of years, unfortunately. So this is so far the best we can do. I have a bunch of projects underway with simulations to try to understand the role of the FTT better, but that's a subject for discussion, I think. Okay, I think I'm out of time. So, okay, so good. So we have these constraints on models that we can also do after we've done the fit. I think this is an interesting one. We can set the strongest constraints to date on a thin, dark disk. So if it's a very thin, dark disk, so this is a plot of the limit we get in a function of the surface density of the disk and the height of the disk. And our limits are shown in pink here. This is the excluded part. And so these are previous exclusions shown here. And so if you go to the very thin limit, at least, we're setting limits that are many or several orders of magnitude stronger than previous measure. So some alternative theories of dark matter have radiative processes that could lead to collapse and formation of a thin dark disk. So we can set limits on that possibility. Okay, I don't have time to go through this, which is actually one of my great loves, anomaly detection. So I will just, you can ask me about that. I'm going to talk to a lot of people, so you can ask me about that. But this is what we can do with bump hunts. We can basically enhance a bump hunt. So if it's just z prime to mu mu, of course, there's nothing for us to say. But if it's a z prime to, say, jets that have internal substructure, then if you do the traditional bump hunt for those jets, you'll miss the new physics, or you will not be as sensitive to the new physics. So what we can do with these anomaly detection techniques that combine density estimation and generative modeling is to learn stuff in the sidebands and interpolate it into the signal region, and then get a very sensitive anomaly score. And after we cut on the anomaly score, we can enhance the significance of a bump. So we can turn something which would be hiding in the data at the 1 sigma, 2 sigma level. We can enhance it to many, many sigmas, so the well above discovery threshold, using the significance improvement idea. So basically, yeah, we take a bump that's hiding in the data, we do a cut, and we make the bump. We reveal the bump. So these ideas are being applied to by Alice and CMS actively, and so these are 3 recent searches that have used these, we call it resonant anomaly detection. And this is a big growth area for them, I think, and there's many new things on the way. A lot of R&D that we've been doing. So it takes the LHC experiments forever to get on an analysis. So in the meantime, we can race ahead, and I see some nodding heads. People here. So yeah, so we can both consult with CMS, and so I'm actually, if you look very closely, I'm a 1 out of 2,000 co-authors on this one, which is a rare thing for CMS. I'm glad to put theorists on their papers. So yeah, so that was a cool experience. And then in the meantime, we can race ahead and produce lots of new improvements and enhancements for these resonant anomaly detection techniques, which then can be further turned into analyses. Okay, and if you want to learn more, these are 2 great references from another data challenge that we organized called the LHC Olympics 2020, which, again, a very valuable compendium for these anomaly detection techniques applied to particle physics. Okay, so I don't have time to tell you about, oh yeah, so we also apply these things to astronomy. Sorry, I'm just jumping everyone now. And we also found some dwarf galaxies with these techniques. So some interesting, they're called field dwarfs. So they're ultra faint. They have very few stars. So they're thought to be dark matter dominated, even more than the usual dwarf galaxy. And they're not processed by any host galaxy. They're just out there somehow floating around between galaxies. So they're potentially interesting for understanding dark matter. And then this is what I've been doing since 2026 or so, is playing around with Claude, but maybe I'll just, it's been a crazy few months playing around with Claude and doing 2 single author papers. I think I doubled the number of single author papers in the last 2 or 3 months. And I wanted to try something out that's sort of orthogonal to all the other stuff I was doing, just because, these are riskier things, so I didn't want to put a student on it necessarily. It might not pan out, and it's sort of orthogonal to everything else. But we found some good success on developing machine learning for symbolic simplification. Like, here's an example of some 5-point Yang-Mills tree amplitude computed with Feynman diagrams, and it's known to simplify to the Park-Taylor form through repeated application of identities. But it's been an interesting challenge. How could we train an ML algorithm to automate this process? And we found an interesting analogy, by we I mean me and Claude, found an interesting analogy to how Rubik's Cubes get solved. And we could think of every complicated expression as a scramble of a simple one. And we actually found a paper that literally did this in the there's a Rubik's Cube literature.
Yes.
So it's an interesting ML problem, actually, to solve Rubik's Cube, also in robotics. And yeah, so that worked really well, and we're also applying this to IVP reduction of Feynman-Lewis integrals. So this is just what I wanted to end with, because I think all the other stuff I told you about can further be enhanced and accelerated using tools like Claude Code. It's especially good at coding and machine learning, engineering, software engineering, machine learning. So it's got a special strength at that. But yeah, this was an interesting experience. It was extremely, and I would love to talk to people here more about that. I think it has huge implications for how we're going to do research in our field going forward, and also how we educate our students and mentor our postdocs. So to not cannibalize the next generation of students and postdocs, I think it's imperative that we train them in how to use these tools. And it will require training, at least as they are now, because they are insanely fast, but I would say highly brain damaged. So if you just give this to a student, you might just get, the quality control could be an issue. So you have to essentially, I think, train the student more and more to act like an advisor without having the long maturity experience of that. So how do we bootstrap that? I don't know. It's not something our undergraduate education is focused on either, So I think, yeah, but I think that could be the future we're looking at. So yeah, happy to chat more about that.
We have many questions. If maybe one or two quick questions.
Just a quick question. So in this last part, was there any new result in amplitudes that you discovered, or you were just checking previous results?
Good. So I think I would characterize it as checking previous results. So we
simplifications.
Tested it out on from this paper by Cliff Chung and Aurelian and Matt Schwartz. They had a test data set of all the 5-point Yang-Mills amplitudes. So they all simplify to Park-Taylor, but they look nasty if you use 3 amplitudes. They had a data set of about 1,000 of these. So we just checked it on all of them, or well, actually a fraction of them, just for the sake of time. But yeah, so we checked that it could figure out how to simplify all of them.
Is there potential to maybe in the future find new results?
Yeah, I'm not sure that the massless spinor helicity scattering amplitude at tree level is like it's not my area at all, but I'm gathering that it's not like the frontier of anything. So I would view this as just a toy demonstration of this technique. And what I'm most excited about is actually this IVP reduction. That's a real bottleneck, is when they do high loop Feynman diagram calculations, and they need to reduce them to master integrals, and they currently run out of memory because of the way they do it. This approach, which does everything online, so at every step it predicts the best action. It has like stable fixed memory usage. So that actually I think we can use this to push their frontier forward very directly. Yeah.
Very good. So probably we should stop at this point and think about it again.
So between archive, Cornell and hiring,
I'm going to send you
the increasing proliferation
I can also send you the.
We should talk for like 5 minutes.
This is already like a huge problem in all the big.
So you're gonna send me the file.
And I'll also send you the Google form.
I literally just hired this guy.
It's like an attitude of keeping you up to date with archives. Need that. Hopefully our field will still go on.
I do think we need to, you know,
So
like
one
time
thing
is
that
of
we
the essence.
noticed that, it's very funding is not quite fixed that.
I actually realized that was me being very biased.
This is from Kazakhstan.
So the standard thing is like I'm actually not sure in space nowadays that a effect that ends.
It's already been listed.
Right, so normally, I'm Lucy Morrison, I will be
You have to put something.
I just had to say, you were hitting like so many problems that I'm working on, but
If you want to chat,
just
I can make time today, but right now, we're not
Yes.
going to be.
So-
There's a
Yeah, so he's starting here at 19. Okay.
So,
No,
so
no,
I could chat.
Yeah, but yeah, no, I think
Well,
other times
like-
today won't work.
Okay,
Unfortunately,
that's the
this
problem.
is the platform. So for me, you know, the obvious
Okay.
question
So one.
acceleration. I think like basically, I think the thing is that we need to settle on kind of packaging.
Okay.
Because the time is of the essence, and to start, you know, putting everything together.
Okay,
And
okay,
results,
okay.
you know, we need at the end of the day.
Okay. So one thing that could be a good exercise that we could do, and then we could also do, it could all be done. Yes, if you have time. Try drafting an outline of what you think are.
You know, and so.
And then if you want to do it.
Then the
Alternatively,
you know, those fragments, all these
I'm happy to do it.
knowledge bases and whatnot.
I'll have a gap today while Rob is eating lunch with the grad students, during which I could draft a rough outline based on the document that you have, and then the two of you can have a look and have a chance. Iterate, and then we can try to meet on Monday.
I think, so I think a useful thing is, like I said, even if it's not all typed out, in the overleaf, have bullet points for like all of the actual calculations.
Stepping stone by stepping stone.
That would be
Because I think that, you know, one of the things is that basically.
Okay.
Yes.
Yes.
Yeah. Because basically, I think we're in a situation where we don't want to sort of work in a new direction and not qualitatively questions. We need to take everything that you actually have done and figure out, you know, what are kind of the unifying themes and comments about this. And there is this, I mean, I spent some time staring at, you know, this eminent symmetry, blah, blah, blah. And you know, there is, I'm sure there's a similar story here. I don't think, I feel like those papers really like beat to death.
It's an
some stuff
upfront
that's maybe not
cost.
that.
Ideally, there's a longer term payoff. But
So why don't I try, how about this?
lots of
Maybe,
exciting
let me try
stuff.
writing it out.
So I saw you're on the schedule for like tomorrow. right?
Tomorrow
Okay, great.
afternoon. Yes,
Perfect.
so-
Okay,
so
looking
great.
forward to it. Thanks.
Thank you.
All right.